So good morning everyone, welcome to Turbulence. We shall continue the lecture. Last time we discussed the ideas of vectors and tensors and how useful they are in formulating equations of fluid motion. We thought of vector as having three components, basically one direction. There's some quantity that has a direction and magnitude, which fully characterizes it. But tensors, we said, are next level of mathematical definitions, which have depend on two directions, so simultaneously. And we talked about the tau, or surface stress tensor, which would act on the faces of a fluid control volume, like wherever that might be. So we should now go back to the equation. So the fluid equation of motion, basically Newton's second law, was shown to you here on this page. So if I scroll down, you can see Newton's second law here. So basically I'm saying mass times acceleration is equal to all the forces acting on the body. So the left hand side is mass times acceleration. If you think about it, density rho is sort of representative of mass. The time derivative of velocity is acceleration. And on the right hand side you have the forces. So what are the forces? The forces are surface forces and body forces. Surface forces are forces acting on the surface of the control volume, like the stress tensor we talked about. Body forces act on all of the individual bits and pieces of the fluid in the control volume. Okay? So you have surface forces, body force, and you have material or total derivative of velocity. So again, as a reminder, we defined gravitational force using the concept of gravitational potential, and we used symbol psi for it. So this is defined as gravitational acceleration times height, z, which would be normal to the surface of the earth. So z goes upward, normal to the surface of the earth, and the gravitational acceleration is pointing down. This is really familiar from mechanics. If you remember, gravitational potential in mechanics is basically mgh, right? So if you drop the m, the mass term, what remains is gh, or gz here. That's a potential. And if you take the gradient of it, as we took last time, whatever that's remaining is g, right? So that's how they relate. If you take the gradient of gravitational potential, you get gravitational acceleration. So that's familiar to us. So going back to the momentum equation, so now I just explained to you, I have psi, the gravitational potential here, and I have the stress tensor. But I don't have the stress tensor on its own, I have its spatial derivatives, okay? Now, let's go back to the index j. Well, index j is just one of the directions within the Cartesian coordinate system I'm interested in. For example, it could be x, y, or z. So what I'm saying is that I can express this equation of motion for any component of velocity. U could be ux, uy, or uz. And we normally use symbols u, v, w for fluid velocities along x, y, and z directions. So j is just a component of momentum of velocity. So let me write this down for you. J is a component of momentum or velocity. J is component of momentum or velocity. so I have the equation. Well, the body force is here. It's not too unfamiliar with us. Well, if you take the spatial derivative of gravitational potential, whatever that is left is gravitational acceleration itself. So if you take derivative of this potential with respect to z, g remains. So that term is not too unfamiliar. It's just some constant in the equation. But the surface forces need a little bit more work. Okay, so, and that's where a lot of the theory is applied to. So that takes a lot of thinking. So now let's direct our attention on the surface forces. For constant property in Newtonian fluids, for example, water, air in short, small scales, we can assume constant density. The fundamental class of flows that we consider in this book are as such. If that's the case, then the surface stress tensor is greatly simplified. It has two components. One relates to the normal components of the stress, which we know as pressure. And the other one is the shear or sideway action on the control volume. If you go back up here, if you look at this diagram, we said on each of these faces there is a normal component of stress, so tau zz here, tau xx here, tau yy here. That's normal to the face, so it acts like pressure. So it either pushes the control volume or pulls it apart. So compressing or stretching. This is the pressure term that I have down here. So these are the pressure terms. The parallel components to the surface, these cause shear or sideway displacement or distortion of the control volume. These I know as shear components, which are very well captured here. So it's only because I have Newtonian flows with constant property that I can write surface shear as constant viscosity multiplied by derivatives, spatial derivatives of velocity. And that's the very assumption for Newtonian fluids, this term here, right? It just relates shear to a constant number we know as dynamic viscosity, or mu. Of course, if you're interested in non-Newtonian fluid dynamics, this is no longer valid. There are fluids that exhibit shear thickening or shear thinning, and this whole relationship is more complicated. But a lot of classes of flows are governed by this, which is nice. So P is pressure. Here P is pressure. And mu is a constant, known as dynamic viscosity. What about this symbol delta, delta ij? Have you seen this before? If you look at the appendix, delta is called the delta function. It's only one if I and j are the same. For example, delta 1, 1 is 1, or delta 2, 2 is 1, delta 3, 3 is 1. But delta 1, 2 is 0, delta 2, 1 is 0. So again, it's sort of like a tensor. It takes two indices, and they must be equal for delta to assume a value of 1. And that very nicely ties into the normal components here, right? If I am talking about a normal stress, that's got to be either xx, yy, or zz, right? That's only in those three components where I'm accounting for pressure. However, if I'm thinking about the sideways components, then delta would not apply, or basically it will be 0. So all I'm saying is, if I'm after tau xx, for example, right? Tau xx. Well, I have a pressure, and that must be accounted for, because tau xx is a normal stress, which is pressure. But if I'm looking at tau xy, delta of xy will be 0, right? So the pressure is knocked out automatically. So now all that's left to do is to insert this definition for surface stress in the momentum equation and derive or obtain a useful Navier-Stokes equation, which we can use. If you did that, if you did that, you get the top equation. So on the left-hand side, I had mass times acceleration. I still have it. Basically, rho, representative of mass, and derivative of velocity, times derivative of velocity, acceleration. I have now all the specific terms. Two of these come from the surface stress tensor, right? The first term here is called surface shear force. That was the sideways action on the surface. So the constant mu appears here. Then I have the normal force. So the pressure is here, and the body force still remains. Now you see I have a second derivative happening here. Well, why? Because in the equation in the first place, there was a spatial derivative of stress tensor. There was a derivative of a stress tensor, but a stress tensor itself had a derivative of velocity in it. So the derivatives cascade down, and now we have a second derivative. Well, again, you should not be confused with the indices. Well, index just means the specific component of velocity I'm looking at. Could be I, x, y, or z, or this could be actually u, v, or w. And again, you could be taking the second derivative with respect to x, y, or z. Now, this type of derivatives, or taking derivatives, or the notation for representing the idea comes from Einstein. Have you heard of the Einstein notation in derivatives? It's in the appendix. If you check the Einstein notation in the appendix, it will tell you how to interpret this type of derivative. Basically, if one index repeats, you apply that for all of the possible components. For example, this, if you want to see what this operation does, well, you're taking second derivative of something, right? But the issue here is index I repeats, right? Because it repeats, you have to apply it to all of the components. Only because it repeats. However, here the index does not repeat, so it's only the differentiation of pressure with respect to the jth component. This could be x. It's only partial of pressure over partial of x, or partial of pressure over partial of y. Only. You don't repeat that. And if you notice, this j is the same j as the component you're looking at. So if I'm looking at the jth component of momentum, let's say x or u, then this would be partial p over partial x. If I was looking at the y component of momentum, if this was v, I would have partial p, partial y. Okay, it's just a very, very, very useful way to write differential equations. It's not only limited or useful in fluid dynamics. They use this in all of physics, quantum mechanics, astrophysics, planetary motion, all branches of engineering. It's a very useful notation. This we also know as component form of Navier-Stokes equation. Why we say component? Because this only relates to one component of velocity, not all. So this only gives you for one. In fact, this represents three equations, right? You could write it for x, you could write it for y, you could write it for z. So there are actually three equations. It is customary to combine the last two terms in this equation. People often do that. And if you combine the two, you get something called the modified pressure. Modified pressure is just pressure modified by the gravitational potential. Okay? So I had pressure, capital P. If I add rho times gravitational potential to it, then I get lowercase p. That's the modified pressure. And if you combine the two, then you can compress or zip your Navier-Stokes equation further. Why? Because now I was taking the derivative with respect to one of the components, x, y, or z, and that applies to both of these terms, right? xj, xj. So it's really taking the same derivative of the combined pressure, modified pressure, right? So that combined derivative in 3 dimensions can be represented by nabla or gradient. Remember, we talked about that? So gradient, nabla, the operator means 3-dimensional differentiation. So I can show this whole operation here with the symbol nabla. I divide both sides of this equation by rho or density, so it's not on the left-hand side anymore. So I have 1 over rho. I'm also doing something else. From the component form, I went back to the vector form. So now this u is a vector. So I'm not looking at the component, but I'm just putting the vector here. So that's boldface u. So that's still, again, back to vector. Gradient we knew would give us a vector, right? And then this second derivative that I had up here in component form, in vector form, appears with this symbol. Okay? This symbol is called, do you know what this is called? This means a second sort of a spatial derivative, second order derivative. It's called the Laplacian. It's called the Laplacian. In the appendix you can check the very definition of it. But anyway, I'm giving the equation for it to you anyways here, so that is the Laplacian. Okay. One other thing that happened is, okay, what is this symbol nu? What is nu? I have nu in the equation above. Do you want to try? Explain that to me. Up here I had mu, but here I have nu.
Divided by density.
Divided by density. So we call this kinematic viscosity. Anytime you divide dynamic viscosity by density, you get kinematic viscosity. It's some sort of viscosity that does not depend on mass anymore, right? So it goes from dynamics to kinematics. So if remove the effect of mass there. And again, this either mu and nu show up again and again and again in fluid dynamics. Anytime you're looking at a dynamics equation, it has a mu in it. Every time you're looking at a kinematics equation, it has a nu in it. So that's all very exciting. Again, u here is a vector here. It's capital. So again, this is sort of a 3D equation. It is very customary to think of ux, uy, uz, or u1, u2, u3 as the three components of velocity. I mean, a lot of us know it as u, v, and w, three components of velocity. That's okay. The condition for continuity still holds. Solenoidal condition still must hold with the constant density Navier-Stokes constant density flows and the associated equations. And that's it. I mean, that is the sort of the master equation that I have up here. This equation has been recognized as one of the greatest equations ever discovered. I mean, this is on par with Einstein's relativity, or, you know, F equal to ma of Newton. It's just as important, and it was discovered simultaneously by Stokes and Navier, or Navier and Stokes, two scientists that discovered this, and it was named after both of them. Okay. All of the action, I mean, all of the development was here. Right? I mean, this was the hard part for them to realize, to come to this part. But this part was not so difficult. Like an average scientist or engineer could do this part or that part. But this third term was the real deal that they found. The equation does simplify substantially. There's a lot of flows in which viscosity is not really that strong or important. So there's the viscous term containing mu is negligible for a lot of flows. Such flows are called inviscid flows. Inviscid, that means not viscous. And that happens for very thin fluids that do not really have lots of viscosity. Flows in the aerospace domain have such flows, like flow over airfoils at the top of the atmosphere, which is very thin, velocities are high. A lot of those applications, you can assume inviscid flow. It's a very good assumption. Of course, in like ventilation science or, you know, sort of hydro engineering, that's not a very good assumption, because water is very viscous, and high pressure air, like we have it here near the Earth's surface at low velocities, is very viscous. But up there, fast velocities, it's a very good assumption, inviscid flows. So if a flow is inviscid, then the term that comes with the contribution of viscosity disappears. Stress tensor is only pressure. So that second term is now dropped out, and viscosity was negligible anyways. So if I wanted to look at the equation, this would be 0 or close to 0. So this whole term would drop out. So that would be the resulting fluid dynamics equation. It's known as the Euler equation. Known as the Euler equation. And in fact, this Euler equation was discovered earlier by Leonhard Euler, the Swiss mathematician. So it's interesting. We found this one. Remember what I said? The hard part was not done yet. So first we found this one, and maybe a couple hundred years later we added the missing part for viscosity, and we found the Navier-Stokes equation. It's very interesting. Euler was a student of Bernoulli, okay, in Switzerland. Bernoulli had its own equation, Bernoulli equation. Have you heard of that one? Yes, that's the next level of simplification. So first Bernoulli equation was found, then Euler was a student of Bernoulli. He discovered the Euler equation, and then a couple hundred years later, the Navier-Stokes equations were found. So the history of things are pretty amazing and fascinating too. Okay? I mean, Euler certainly deserves to be underlined. He's a favorite mathematician of most engineers. He's also the founding father of this number, which you know. Right, so Euler said, yeah, let's use symbol E. And we all use it now. So he's quite a figure. Now, so that's good. Any questions so far? Do we only need to solve the equation of momentum if you're doing fluid dynamics, or there's more to do? Are we only concerned about momentum? Or there could be other things. Of course, there could be other things, right? There's other things that are being moved around and transported, such as temperature, energy. You also want to study dispersion of some material in a fluid domain, right? People in air pollution do it all the time. So there are more equations to solve. There's not just momentum and continuity, okay? And depends on the application. One of the ones I want to discuss with you now is the conserved passive scalar equation. So these are things like pollutions, tracers. You leave some sort of a smoke here, and this smoke is going to move around the room or the atmosphere. So you release some sort of a chemical in the fluid, some substance, and it starts dispersing. So that's what we mean by scalars. Well, we say passive scalars. Why would we want to use the term passive? There's a good reason with that. Let's say air is flowing in this room, right? So I move my hand. Air moves with my hand, right? Okay. Air moved in some way. Let's now say I still move my hand, but I release some smoke here, right? And I move my hand again. Would motion of air change with or in the absence of the smoke? Probably it's the same, right? Air doesn't care if there's the smoke or tracer in the background. It just moves the way it should move with the sort of momentum of my hand, with the boundary conditions on it, and right? So it doesn't matter whether or not you have the passive scalar. Air does its thing. It moves in the way it wants to, right? So that's why we say this scalar is a passive scalar. It's passive. It's not actively changing the momentum of air. It's just passive. It's just sitting there, right? Air doesn't care. It's sort of, think of it this way. It's a one-way influence. Air influences movement of smoke, but smoke does not influence movement of air, right? So it's just passive. Although that's not true for all other transport equations. Other things can happen. If you solve for energy equation, that is a two-way relationship, right? If I have, like this light here generates some heat, and there's a thermal plume, right? So heat, source of heat, causes air motion in a certain way. It's tightly coupled with momentum. So that we don't call a passive energy equation. There's no such a thing. It's the coupled energy equation. So it's a very important concept. The Navier-Stokes equation can be extended to express the transport of conserved passive scalar. So think of it as some sort of a pollution or chemical or substance. It could be CO2 releasing from my speaking in this room or your breathing. We designate the term phi for the passive scalar. Think of it as concentration. Concentration of CO2 in this room is something at any location and time. So x was position vector, time is time. So phi would depend on both space and time. In constant property flows, the conservation equation for phi is given in a somewhat similar fashion as we had momentum, but simpler. Well, on the left-hand side, I have time derivative or total derivative of passive scalar or concentration. On the right-hand side, I only have one term. That's called the diffusion term, and it's a Laplacian of the concentration. That's all. There's no pressure in here. There's no viscosity, viscous term in here. It's just a diffusion term. But the question is, what is this symbol? Do you know what this is called in Greek? It is gamma. It's a capital gamma. I mean, certainly if you're doing engineering, it's not luxury, it's necessity that you have to use all these symbols because we run out of symbols very quickly, right? So gamma, it's the Greek symbol gamma, which is known as the constant, and it's basically uniform diffusivity. Diffusivity, some constant that determines how fast, strong something diffuses in space. So that's all I have to say about the passive scalar equation. We will certainly do a lot of problems with the problem sets with that. They are coming up, and I'm going to expand the material derivative for you. I mean, I haven't done it yet. I haven't told you what the material derivative is. I'm yet to expand the left-hand side for you as well, which I will in shortly, I would say. The question is, what is this diffusivity? How do I calculate it? It is related to kinematic viscosity. When the passive scalar is temperature, I mean, you could consider temperature as a passive scalar. I mean, by definition, you may assume temperature, if its variation is very moderate, is not influencing momentum. So it could be, under very limited conditions, considered as being passive. You could do that, although if temperature gradients are high, then it's not passive anymore. But one level of approximation is to assume temperature is a passive scalar. It could be under very special cases. The diffusivity is called the thermal diffusivity. Okay? And it's non-dimensionalized using the kinematic viscosity in the so-called Prandtl number in honor of Ludwig Prandtl. Ludwig Prandtl was the grandfather of boundary layer theory. He's a German engineer. And he came up with this. He said that the way momentum and heat diffuse in the fluid domain are not totally independent, they're related. And he expressed the relationship as such. So basically, the ratio of the two is some number for a given flow, Prandtl number. So if you divide kinematic viscosity by heat diffusivity, you get this number. Alternatively, if you had that number the Prandtl number, you can calculate heat diffusivity by dividing kinematic viscosity by the Prandtl number. And I can give you an example. For air, Prandtl number is about 1. It's a good approximation. Approximately. Of course, it could vary if you're close to a wall, if you're away from the wall, if Reynolds number is low, if Reynolds number is high. There are those variations, but by and large, order of 1, Prandtl number is a good assumption. I should remind you, I'm not talking about turbulence yet, right? This is just laminar fluid dynamics, so there's no turbulence. Everything is laminar. And all of these terms refer to sort of molecular diffusion. You know what I'm saying? Not diffusion caused by fluctuations and chaos. No, just molecular. Another way to define passive scalar is consider passive scalar as a concentration of some tracer species, the CO2 example that I used. In that case, the diffusivity is called the molecular diffusivity. It's not heat diffusivity anymore, it's just molecular. It's how a species move through bouncing molecules. And it's non-dimensionalized using the so-called Schmidt number in honor of Ernst Heinrich Wilhelm Schmidt, who was another German engineer, overlapped with Prandtl, and came up with the Schmidt number. And I can show to you that way. So it's very similar form. Here I have gamma still represents diffusivity, but not heat diffusivity. In this case, molecular diffusivity. And then the ratio of kinematic viscosity to this molecular diffusivity is the Schmidt number. Or alternatively, if you have the Schmidt number, you can calculate the molecular diffusivity. If you do the type of work that I do, these two numbers come up all the time. Schmidt number and Prandtl number, all the time. Because in my group we do studies on air pollution and dispersion. There's some sort of tracer that moves around we want to study. The concept of Schmidt number comes up all the time. We also solve problems that involve heat transfer, like convective boundary layers, stable boundary layers, temperature gradients, ventilation flows, displacement ventilation, all of those things. There's always a temperature gradient for which the Prandtl number comes up. And a branch of science goes into studying a Schmidt and Prandtl number. There's a lot of scientists that actually want to understand what these numbers are, and they're not sort of constants, right? It's not like density, right? Or heat capacity of some substance. These numbers depend on the flow. You see what I'm saying? You could have high Reynolds number flow. You could have low Reynolds number flow. You could have spinning flow. You could have atmospheric flow. You could have supersonic flow. You could have all kinds of flows, near walls, away from the wall, jets, shear layers, plumes. These numbers change given the flow of interest. Okay, so you have to be careful. So as I said, the Prandtl number is in the order of 0.78 for air, let's say. So is the Schmidt number. But it could change it could change considerably given different substances and so on. For example, for helium it's 0.2, the Schmidt number. But for octane it's 2.6. The type of material also specifies what it should be. So far so good. Again, very fundamental. I mean, I'm just sort of touching the surface, but I'm not opening the hood and going down deep. Right? I'm just sort of putting the idea out there, but we will go deep in the coming chapters in each of these concepts. The next concept is vorticity. Have you heard of the term vorticity? What is vorticity? manic, right?
Yes.
Yeah. What is vorticity? Spin.
Circulation times 2.
Circulation.
Something like that.
Yeah, circulation. Has something to do with the spinning motion of fluid. Now, why am I caring to define this? Because we told you about eddies last time, that turbulence manifests itself as formation of eddies or a spinning structures of fluid. So, but a spin is qualitative definition, right? You are asking, okay, how do I calculate mathematically? There is a way. You can mathematically calculate the degree of a spin or circulation, Scott said, in fluid. And the way it's done is by vorticity. If you take the curl of the velocity vector, you get vorticity or spin. Now again, curl is a calculus definition. You can go to the appendix to see what it is. Basically, it's some sort of a cross product of the nabla or gradient operator with a vector quantity. I should remind you, this is still velocity vector. It's a 3D vector, the 3-component vector. So is vorticity. Vorticity is also a vector, which means it has 3 components, right? I mean, loosely speaking, let's say this is Z. This is the Z-axis. If I have something that spins around the Z-axis, it has a vorticity along the Z component, or WZ, but it has no vorticity around the other components because it only is spinning around the Z-axis. But some object may spin in more complicated ways. It could spin along one axis and at the same time spin around some other axis too, right? In that case, there would be some other components of vorticity. Vorticity is a vector, so it has Wx, or omega x, omega y, omega z. So it has 3 components. If it's a vector in 3D space, it must have 3 components. And we use the symbol omega to show it. It's, I think Scott alluded to, is equal to twice the rate of rotation of the fluid at any given space and time. So it could depend on both space and time. X is vector and t time is scalar. What's really fascinating is you can think of vorticity as some sort of a property of fluid independently, right? It's circulation or spin, right? It's some property you can think of and you can analyze and you can calculate. I mean, the analog would be in dynamics where you have linear motion and you have angular motion, right? People out there write equations of angular motion, like there's moment of inertia, there is angular acceleration, and the F equal ma has a counterpart for angular motion, right? Which is torque is equal to moment of inertia times angular acceleration, something like that, right? Same thing here. You can write the F equal to ma of vorticity, or torque equal to moment of inertia times angular acceleration of fluid dynamics. You can do that. And if you do that, this is the equation you get. Now the variable of interest is not velocity vector anymore, it's vorticity vector, spin. And the time derivative of that, the material derivative, is then equal to 2 terms. Diffusion of vorticity plus vortex stretching. So things start getting a little bit abstract. But if you start with the Navier-Stokes equation for momentum and you take the curl of it, you will get here to this point. I'm saying if you take the curl of this equation, right, this was the momentum equation, have a nabla cross the left hand side equal to nabla cross of the right hand side. It's just a calculus exercise. You can do it if you want to. Then you get this following equation. So surprisingly, the term, the Laplacian, showed up again as a diffusion process with kinematic viscosity nu, which means that vorticity kind of diffuses. It's kind of fun to think about. If you spin a piece of fluid, it doesn't stay here. It sort of diffuses into the background. It's really fun. But it also stretches. This spinning motion can stretch in different ways depending on what the flow is happening around it. Especially if, like, put a blob of spinning fluid in place of flow, it will be stretched. I mean, if you go swimming, you can try these things. Have you seen people start a vortex in a swimming pool and watch it move around? It's that kind of stuff. You can start one and then put it in front of flow. It will be stretched. Eventually it will diffuse. But it's really fun to think of it as an independent property. Another fascinating part is if you take the curl of the momentum equation, the pressure term disappears. The pressure term in the Navier-Stokes equation vanishes. And that's just a calculus fact. It's a property of vector calculus. If you take a gradient of something, and if you take the curl of the gradient of something, it will be zero. It's guaranteed to be zero. Okay? So, that's really fun. So again, when we talk about turbulent eddies, we really mean a blob of vorticity and its associated rotational and irrotational motion. So vorticity is the very definition of eddy. So anytime somebody says vorticity in turbulent flow, think of eddy and think of chaos, think of fluctuation. It's so true. Are you excited so far? Right. I hope I'm not sounding too abstract. Things will fall in place. Fluid element deformation. In solid mechanics, things usually don't deform substantially unless the bridge collapses and or the building by earthquake falls, or if there's deformation, there's like elastic deformation, which is very minimal. You pull a cable, it elongates using the stiffness factor and things like that. So deformation is very minimal in solid mechanics. Whoever does civil engineering and things like that. But in fluids engineering, deformation is a serious business. It happens all the time for all fluids. In fact, in most fluids, there is deformation in the fluid element. It's a very abstract concept. Because, well, really, in the real sense, fluids are molecules, and molecules move around. I mean, molecules don't deform, right? There's a bunch of water molecules in your Archimedes screw. Molecules, things don't deform. But what is deforming then? If some substance is a bunch of molecules, what's deforming? Right? The problem comes from the way we analyze these systems, right? When we talk about deformation, is the way we analyze and we imagine the unit of the fluid as we like, and we can calculate. When we do calculations using Navier-Stokes equations, we don't calculate momentum or motion at molecular level. We calculate motion at some other small discrete value, which we know as control volumes. See what I'm saying? So the concept of deformation comes up with the concept of control volume. It's arbitrary, it's abstract. It's the way we define, formulate, and solve fluid dynamic problems. I mean, anything in physics can be thought of that way. I mean, acceleration. What is acceleration? It doesn't exist out there. It's the way we interpret motion. Everything in physics is the way we see things, right? It gets very philosophical. But anyway, let's stop there and say that fluid elements or control volumes, as we looked at before, deform in flow situations. And they deform in very complicated ways. However, if you break it down, deformation is only possible in 4 sort of categories. A lot of the times, fluid elements just translate, just move from one location to another. You think about it, there is tea in my mug. I just moved this a little bit here forward. That control volume of tea fluid here did not do anything else but translate. There could be linear strain. Well, you could just stretch a control volume, right? In which case, the fluid will stretch or compress, stretch from one side, or maybe compress from the other side. I can't do this to this mug, right? Or it will break. But if you think of, I could just stretch, elongate the height, and shrink the cross-sectional area, right? I will stretch the T in this. There is shear strain, right? Which means if I apply the side wave action or shear action on the control volume, like this represents, from a square I get a trapezoid. So this is kind of a shear strain action. I could also rotate. The control volume. Like think of this mug, I just rotated all of it. Right? So any fluid deformation, as we formulate fluid dynamics, is one or a combination of the 4 possibilities here. It's a very nice and profound concept. And when you combine all 4, maybe different relative effects or magnitudes of each deformation, you get a total combined deformation, which is then maybe something like that. It translates as well as stretched, as well as shear strained, as well as rotated. Okay? So that's the first concept. The next concept here is these deformations are related to fluid velocity around the control volume. How? Think about it. If this control volume want to translate, every parcel here on everywhere should move with some velocity ux and maybe uy. Every fluid molecule in that control volume should move with some velocity x in the x direction and some velocity y in the y direction. So eventually, this whole thing is translated. So everywhere, if you look everywhere, all the molecules of fluid in this control volume is moving by some velocity. So eventually, it will translate. But not always. I mean, if you want to shear strain a fluid element, you should apply different velocities, right? I mean, here, for example, in the x direction, ux must be 0 on this face. So the bottom surface of that control volume doesn't move, but the top surface should move with some velocity ux. There shouldn't be any uy. You see what's happening? So it's the differentials of velocity that cause deformation. fluid volume. So the concept of deformation is very, very tightly related to velocity gradients. So let's sort of underline a few keywords here. The velocity gradient, and when I say gradient of velocity component I with respect to velocity space component j, I mean, I could be talking about anything. I could be talking about partial of u over partial of x, or partial of u over partial of y, partial of v over partial of z. These components could be anything. So these are components of a second order stress tensor. For constant density flow, the composition of these velocity gradients is possible into symmetric, deviatoric, and antisymmetric parts, or asymmetric parts. Now, see my goal is to tie in the concept of velocity gradients to deformation, right? I'm doing this now mathematically. I can say any deformation, right, any velocity gradient, let's say I and j, can be decomposed into two components: symmetric deviatoric deformation and antisymmetric deformation. Note that these are tensors. Why? Can anybody say why is this one? I'm thinking of it as a tensor. Two. It has two in this, or multi-directional, if you like. It has I and j. So S is a tensor. What is this symbol called in Greek? Omega, capital omega, right? Probably you're a fan of the watch that you all know this. The favorite omega. This is also a tensor. So somehow I'm expressing this derivative or deformation as a summation of two tensors. That's how useful tensors are. I mean, you could do a lot of things with physics. So let's see what they are then. The first one we know as the S, or symmetric deviatoric, we know as rate of a strain tensor. You can think of it as, it's just by definition, right? I mean, you can't prove this, just definition. Is 1/2 of the gradients of velocity in such a way, or gradients of deformation in such a way. So if I take gradients of ui xj plus the opposite, uj xi. So I'm just switching the index. I get rate of strain tensor, which means I get, let's say, partial u partial y plus partial v partial x, for example. And it turns out that this kind of tensor very well characterizes this type of deformation. This type of tensor always has to do with shear action. It will sort of slide control volume sideways. The other one, omega, the antisymmetry, is the rate of rotation. So now I'm doing the same, but I have a negative sign here. So again, 1/2 of the partial ui partial xj minus partial uj partial xi. So this could be, for example, 1/2 of partial u partial y minus partial v partial x, for example. And I just put it in a way that at the end I do get the deformation if I added them up. Let's see what happens. If I add, let's start from here. If I add I add the two, that's what I had up here. If I add these two, you get 1/2 of partial ui partial xj plus partial uj partial xi plus 1/2 of partial ui partial xj minus partial uj partial xi. And the negatives cancel. I only have partial ui, partial xj left at the end. So that's what I claimed it to be up here, right? And it is, right? It's just, it should not surprise you, let's put it this way. I just defined it to be that way. I just wanted you to see the relationship. Okay, so that's by definition. And it's the second one, rate of rotation. If you look at these gradients with a negative sign, they express some sort of a rotation, and that's why we call it rate of rotation tensor. Right? It's really fun. It really does. So any deformation if you like, can be thought of as some sort of a strain plus some sort of rotation. That's how generic it is. Okay. Any questions on that one? Now let's tie this back to the Navier-Stokes equation. I showed you the surface stress tensor before, tau ij. Well, the first one we agreed would be the normal component pressure times the delta function, the negative sign. Now you see, the second one, I am rewriting with the strain, rate of strain tensor, as opposed to the components separately. I showed you this equation before. If you're not convinced, I can pull it up. Right? If you go here, I showed you this equation, remember? It's right here. Do you remember this equation? It's the same equation. But I'm just saying, okay, what I defined for you here as this sum came up, and it is the same as my definition rate of strain. So I'm just replacing that with S, but there's a factor of 2 because there was a 1/2 in the definition of S. So the 2 and the 1/2 cancel one another, and mu is still there as the, what type of viscosity?
Mu.
Dynamic viscosity. That was a quiz. So rate of strain. Also, vorticity. You might say, okay, what happened to rate of rotation? Of course, it's there if you want to use it, but that becomes handy and useful when you want to express components of vorticity or omega I. I'm being ambiguous. Okay. Now the question is, what is this symbol then? Epsilon. And in math, calculus, we know this as the alternating symbol. It shows up all over the physics. I mean, another place it shows up is quantum mechanics. Anytime that you work with differential equations, it comes up. It's just like delta. It's just some sort of a remembering tool. If you think of ijk as 1, 2, 3 for x, y, z, right? This, you want to determine this alternating symbol. It takes 3 indices, ijk. It's either 0 or 1, or positive or, sorry, it's either positive 1 or negative 1. If these indices are ordered 1, 2, 3, 2, 3, 1, 3, 1, 2, sort of counterclockwise, this takes a value of positive 1. So think about it. Epsilon of x, y, z is 1, plus 1. Epsilon of y, z, x is 1. And epsilon of z, x, y is 1. Because I'm going around this circle counterclockwise. But the other possibility is this. If you go around this circle clockwise, clockwise, epsilon is negative 1. For example, epsilon of 1, 3, 2, or think of it, epsilon of x, z, y is minus 1. It's just a fancy way to remember, put together a bunch of positive and negative terms in a somewhat orderly fashion. Okay. In fact, you can use the alternating symbol to define cross product if you want to. So, you don't need to memorize any of this. But I would be doing injustice if I didn't introduce this to you. Because higher level courses and books you may read, these things show up all the time. And of course, you could express circulation, rate of rotation strain as a function of vorticity. You could if you want to, because you just rearrange this. However, you can easily do the same for rate of strain because there's the pressure term here, so it's a little bit more complicated. So what I did here for you so far, I just laid the foundation and introduced the symbols that we're going to use in the following chapters. I introduced to you the equations of momentum, continuity, momentum, and vorticity. And I told you all the specific terms, one by one, what they are. And some sort of relationship between those terms and what happens to the control volume. The last component in this chapter is the component of similitude, and that will be the final one, so let me introduce to you. A lot of the times in fluid dynamics, we want to know if two flow systems behave in the same fashion regardless of their size or properties. It ties into the concept of scale modeling a lot. You can analyze a phenomena at full scale, let's say the atmosphere, or you could reduce the scale down to a wind tunnel, or the ocean or a river at full scale, or reduce it down to a water channel. The concept of similitude comes up in these situations. So we want to know which two flow systems are essentially the same, okay? Regardless of the size or property. If two flow systems want to be the same, they must meet 3 criteria. First, they should exhibit geometric similarity, which means the relative scales of the dimensions of the system must be the same. For example, this is a full scale cup. If I want to scale it down, I should make a miniature cup. But all the aspect ratios must remain the same. The shape must be. If I zoom into the small cup, if I showed it to you, you should be confused not knowing if it was a scale cup or the actual cup. So geometry, the geometry or the relative scales in the geometry must be the same. So that's condition 1. The other one is kinematic similarity, which means if the paths and moving particles are geometrically similar, and if the ratios of the velocity of the particles are similar. So now I'm talking about motion in the system. The ratios of velocities in the two systems must be the same. If in the big one, on the top of the domain, let's say the velocity was 10 meters per second, the top one for the scale model was 1, that's a ratio of velocities. The ratio of velocities should be the same everywhere in the full-size phenomena or the scale model. The ratio of velocities should be the same. Finally, the dynamic similarity between the two systems when forces at corresponding points are similar. Okay, so that means, again, the ratio of forces everywhere should be the same. And it's a very powerful concept, and we apply this all the time. I think I want to show you what it would imply to Navier-Stokes equations and the similitude. If two systems are similar, their transport equations must look the same, which means the Navier-Stokes equation for flow, momentum, let's say in the full scale, must be the same as the transport equation in the small scale model. So this is called the transformation properties of Navier-Stokes equations. That means if you take the equation for the full scale and somehow normalized it, it would look exactly the same as normalized Navier-Stokes equation for the smaller scale or other scale model. In fact, it's the same equation that gives you the similarity of flow between the two. Right? Otherwise, how could they be similar? So what you do, you usually, I'm going to be very brief, you consider a system with some characteristic scales. Usually it's a length scale. We use that example for the size of this room. Let's say the height of the room is the fancy L, and the characteristic velocity, the fancy U, gives you the representative velocity in that system. And if you took those two characteristic scales, you can non-dimensionalize all of the variables in the Navier-Stokes equations. For example, you could divide all of your positions, x, by that scale, length scale. As soon as you do that, you get a non-dimensional position vector, which is sort of non-dimensionalized. The unit is not meters anymore, or inches or feet anymore. So if you divide that with L, you get that. Likewise, time, you could multiply by u and divide by length scale. Multiply by velocity scale, divide by length scale. Then you get non-dimensional time. So, and these are hats, right? X hat, t hat. So then you get non-dimensional time. Likewise, velocities you can non-dimensionalize. Now velocity itself is no longer a function of x and time, it's a function of non-dimensional position and non-dimensional time. And if you divide the actual velocity by the velocity scale, you get non-dimensional velocity. Now u is hat. Pressure, same thing. Now you divide by density times velocity squared. If you did that, that gives you the unit of pressure, and then your pressure will be non-dimensionalized. And what's really exciting is that you can rewrite the Navier-Stokes equations and the continuity equation, and they look the same. So this is the same as me saying that the continuity equation is satisfied. It's the same thing I'm saying here. And that's the same equation for momentum. But what's really exciting is that now I only have the Reynolds number as the term in this equation. Everything else is non-dimensionalized. The only non-dimensional number is Reynolds number, which we looked at before. It's the same familiar Reynolds number is velocity times length divided by kinematic viscosity. And then that means that I only have to match the Reynolds number between the fullest scale and the smallest scale to be able to claim that the two systems are similar. Think about it. Flow in this room has a Reynolds number, right? It's only momentum and continuity equation. I make a small scale replicate of this room, like this big. If I can manage to have the same Reynolds numbers between the actual room and this small room, same geometry, same similarities, then the flow will move in the same way between the two. It's very, very fascinating. That's the bedrock foundation of scale model engineering. I think you're doing that for the Archimedes screw too, right? I mean, what you have in the lab is not the full scales. So you have to correctly dimensionalize and solve the scale model of that phenomenon. I would very quickly do one problem from this chapter to really nicely, it's a very short problem, to really nicely finish this chapter and be ready for chapter 3 next time. I just want to do exercise number 2 here. So for a simple shear flow, I'm giving you a velocity vector as u equal to y times unit vector I. And I'm asking you to calculate rate of strain tensor and rate of rotation. I just want you to show me that they're actually, both of them are equal to 1/2. It's a very quick problem that I want to do. So that's exercise 2. Exercise 2. The flow is two-dimensional if you think about it in the x and y plane. The flow looks like this. Velocity is only in the x direction or I. U is equal to yi. And if I want to find rate of strain, Sij, tensor is by definition 1/2 of ui which would be simply ux divided the partial ux by partial y plus partial uy partial x. And it's going to be 1/2. I have to take the partial with partial y of y plus partial or partial x of 0. There's no y component in this flow, right? And if you agree with me, partial over partial y of y is just 1, right? So that's 0, that's 1. So the rate of strain for this flow is 1/2, which means control volumes are strained. They are deformed sideways. And likewise, you can show rate of rotation is also 1/2, which means in the same flow, fluid elements are at the same time rotating or being deformed in the rotational sense. Okay? Just wanted you to see how the mathematics actually simplify to some sensible results which you can understand and analyze. Sounds good?
Yes, sir.
Yeah, please try these problems and do come see me in office hours so you are ahead of getting prepared for understanding the course material and the term tests. Any questions? Sounds good. So we'll see you next time.